Okay, in Unit 5.4 and 5.7, we talked about elementary steps, rate mechanisms, and collisions that had to occur, either unimolecular, bimolecular, or TER. We'll go in a little more detail about these collisions today. So we could look at, on top of just looking at the how collisions occur, we can also look at graphically about these rate mechanisms and these talk about these collisions. So rate of reaction directly proportional to the number of collisions. So if you would heat a mixture of chemicals up, they would start to go faster. If they're moving faster, they're going to collide more often. If they are able to react, those frequency of collisions will result in more reactions taking place, so a rate of reaction would increase. Collided molecules form an activated complex. So that's a vocabulary for you there. So it's a transition state. These two reactants have to come together. They're not quite products yet. Maybe something will occur with those products. Maybe they will combine. Maybe they'll just reconfigure themselves and make two products. For any of these collisions to result in a chemical reaction, you'd have to overcome the activation energy required in that particular reaction. And that particular activation energy is related to how much energy is required to break the chemical bonds in the reactants. Okay, so minimum amount of energy required to initiate a chemical reaction. So many times chemicals run into each other, and they maybe would often react, but they don't react. So an example of that would be, whoops, we don't want to use that. So hydrogen gas plus oxygen gas making water. Well, this isn't, now it's balanced, but often hydrogen and oxygen gas run into each other, collide with each other in the atmosphere, but they don't have enough activation energy to break the bonds inside of hydrogen gas and oxygen gas to result in chemical reactions to take place. So again, you need the collisions to occur. The collisions have to be oriented correctly, and then there has to be enough sufficient energy to be able to break those reactant bonds. So I think I just mentioned really collision theory already to you. So we mentioned the frequency of collisions. So what could impact that? Lots of things could impact that. Temperature is definitely one. Another one would be if you would have more chemicals. So that might be grinding a chemical up into a powder. It would result in more particles. You could actually add more molarity, so you'd have more solute in that volume, and any of these things would increase the collisions for sure. And then orientation, like I mentioned, is extremely important. You need to be able to contact the other molecule in the place where the reaction would be taking place. So many chemical reactions don't take place because maybe they have enough energy. Maybe they do collide, but they don't collide in the right orientation. And then we talked about overcoming activation energy. So all those things have to take place for the reaction to actually occur. So what would one of these look like? And we could use these diagrams here, these graphs, to talk about thermochemistry, but today we're going to use it to talk about activation energy. Energy of activation is how it's actually labeled on these graphs. And so these are reactant, these are the reactants actually. And so that's its plateau starting energy. Enthalpy is a form of energy. Well, it's a discussion of energy for us here. And then these are the products. Oh, so it actually is the synthesis of water that I mentioned earlier. And in terms of thermochemistry, because the energy from reactants to product goes down, energy is released. And we'll have other units where we talk about that. So that's the energy released. And that's important, very important. But today, this is what is important to us. So let me erase all these things here. So the plateau to the top of the peak is the activation energy. If we would have the opposite reaction, we don't, but if we had the opposite reaction, it would be from the plateau to the top of the peak. So it definitely appears that there's less activation energy for these reactants to become those products as opposed to those products becoming those reactants. Okay, so again, today we're interested in the activation energy. So we could look at the same reaction in the opposite format, which I had already mentioned. So again, it's the plateau to the top of the peak. Sometimes we have mechanisms. Remember, we have multiple steps. So we have two NOs going to N2O2. So looks like that process is slightly exothermic, losing a little bit of energy in that process, has a tremendous amount of activation energy. I guess we could call this like activation energy 1. Let me erase all that. And then we have the N2O2. It combines with some hydrogen. Again, has activation energy. That's the activation energy this time. And I guess we'd call that 2, since we have two different steps. And so they don't have the same, these two steps don't have the same amount of activation energy. And it's not stated here, but let's state this now, is that we could determine which of the steps are slow and which of these steps are fast. I believe that's the slow step. Whoops. And that's the fast step. Why? Because step 1 has tremendous activation energy. Step 2 has a lot less significant activation energy. So this is probably going to occur faster, and this is probably going to occur slower. Okay. We've already talked about overall reactions, just getting things to cancel. So we got two NOs, and we have an H2 making N2O and H2O. Okay. I think that might be about it. We have a little bit more of, I think we've talked about Maxwell-Boltzmann in the past, and these are about probabilities. And this just shows that at higher temperatures, this curve is the flattest of the three because it's the highest temperature. So in 100 degrees Celsius, you still have an average kinetic energy. Yes, there are some molecules with very low kinetic energy, but there's lots of molecules out here that have high kinetic energy. And at 100 degrees Celsius, because this curve is a lot flatter, you're going to get many, many, many more items over here distributed to the right side, and it's sort of arbitrary where this line is, but this line is our activation energy kind of idea. If any collisions occur over here, they don't have enough energy to overcome the activation energy, break the bonds in the reactants. Reactions don't occur. Any collisions that occur to the right out here, the reaction now has potential to occur as far as energy is concerned. They still have to have the correct orientation. So all this is really showing you is that at 0 degrees Celsius, the curve isn't very flat, and the majority of the collisions aren't going to be to the right of that activation energy idea. As you raise temperature, the curve gets flatter and flatter and flatter, and therefore you're going to have more collisions to the right of our arbitrary activation energy threshold.